All right, if you've got a math exam on the horizon, you're going to want to pay close attention. We're going to dive into the crucial difference between a subset and a proper subset. And you'll definitely want to stick around because I'm going to show you a simple formula that honestly feels like a superpower when you're racing against that clock.
Okay, let's start with a super simple idea. You know those Russian nesting dolls, right? Or maybe just a set of boxes you store one inside the other? Well, that's pretty much the core idea we're talking about here. In math, we just call them sets. Get this one visual in your head because it's the foundation for literally everything else we're about to cover.
Okay, so how do we take that box inside a box idea and talk about it with, mathematical precision? Let's get right into the formal definition.
So here it is, the official rule. Set A is a subset of set B if every single element in set A has to also be in set B. And take a look at the symbol here. See how it kind of looks like a less than or equal to sign? That's not an accident. It's a fantastic way to remember what it means. It tells you that set A can either be smaller than B or it can be exactly the same size as B.
All right. Now, there are two fundamental rules here that you absolutely positively have to burn into your brain, especially for exams. First up, the empty set. That's a set with literally nothing in it. It's a subset of every single set out there. No exceptions. And number two, every set is always a subset of itself. Yeah, they might feel a little weird, almost like trick questions, but trust me, they are core foundational principles of set theory.
Okay, so we've got the basics of subsets down, but now we're going to sharpen that definition with the really crucial distinction, the proper subset. And this is a tiny detail where, honestly, a ton of people get tripped up.
So let's put them side by side. Here is the single most important difference. A regular subset, the one with a little equals line underneath, can be identical to the larger set, but a proper subset, notice no line underneath, cannot be equal. It's a strict rule. It absolutely has to be smaller. That means the bigger set has to have at least one element that the smaller, proper subset doesn't have.
All right, so we know how to spot individual subsets, but what if we wanted to, collect all of them? Like gather up every single possible subset of a set and put them all in one big container. Well, that's exactly what the power set is for.
The power set, which we write as P of A, is basically the master collection. It's the set of all possible subsets you can create from another set, A. Think of it like a recipe book that lists every single combination of ingredients you could possibly make, including using no ingredients at all, that's the empty set, and using all of them, that's the original set itself.
Okay, let's make this super concrete so it's not so abstract. Let's say our set A is just 1, 2. Super simple. What's its power set? Well, it's a new set that contains 4 things. You've got the empty set, you've got the set that just has the number 1, the set with just the number 2, and of course, the original set with both 1 and 2. See? It's just a complete list of every possible combination.
Okay, so a set with 2 elements gives us 4 subsets. But what happens if we add just one more element? So now we have 3. Suddenly, the number of subsets jumps. It doubles to 8. You can probably already see where this is going. Trying to list all 8 of those out by hand, it's starting to get tedious, right?
And it gets worse. Add one more element for a total of 4, and bam, the number doubles again to 16. Can you imagine trying to write out all 16 of those possibilities during a timed exam? No way. There has to be a shortcut, right?
Well, of course there is. This doubling pattern isn't a coincidence. It leads us to a beautiful, simple, and elegant shortcut, probably the most important one in basic set theory. This is the formula that's going to save you all that time and frustration.
And here it is, the moment you've been waiting for. The total number of subsets is simply 2 to the power of n, where n is just the number of elements in your set. So, why 2 to the n? Well, think about it this way. For every single element in your set, you have 2 choices. It's either in the subset you're making or it's out. 2 choices for each of the n elements. That's it. It's clean, it's lightning fast, and it works every single time.
So let's put this into practice. Imagine you're in an exam. The question asks, how many subsets does a set with 5 elements have? You don't start listing them out. Nope, you just think, okay, 2 to the power of 5, you do it in your head, it's 32. Boom, done. Next question. It's really that easy.
Okay, this formula is a game changer, but it comes with one very, very common trap. If that tricky exam question asks for proper subsets, not just subsets, you have to make one tiny adjustment, but that tiny change makes all the difference.
So the formula for the number of proper subsets is almost the same. It's 2 to the power of n minus 1. So the big question is, why are we subtracting that 1? Well, think back to our definition. A proper subset, by rule, cannot be equal to the original set. So that minus 1 is us literally just taking that one possibility, the set itself, out of the total count.
So your mental checklist for these questions should be super simple. Just 2 steps. Step 1, find the total number of subsets, which is always 2 to the n. And then step 2, if the question asks for proper subsets, you just subtract 1 to kick out the original set. What's left is your answer, the number of proper subsets.
Look, I really can't stress this enough. You have to read the question carefully. Is it asking for subsets or proper subsets? Because that one little minus 1 is the detail that separates a correct answer from a wrong one. It's where so many people lose easy points on an exam. Don't let that be you.
So there you have it. You've now mastered how sets can live inside other sets, and more importantly, how to count them in a flash. But here's a thought to leave you with. What happens when sets start to overlap, when they interact with each other? Well, that's a whole new ballgame. That's the world of unions, intersections, and complements, and that's exactly where we're headed next.